our series of training on robotics inspired science education. In our previous lesson, lesson 14, we looked at error prediction and avoidance, and the principle was explained using derivative controllers. In this session, we will be looking at how to implement error prediction and avoidance using the derivative controller, programming with the Lego Mindstorm EV3 programming environment. So I'll fast forward to the formulations or the formulas that we came up with in lesson 4, and then switch to my programming environment. That is what we had in lesson 13, which was proportional controller or error detection and correction. So we will add the error prediction and avoidance to this program. So what we have here is a default speed at which the motors will move when there is no error, a proportional gain that we use to scale the error that had been detected in order to correct the motors. We came up with our error formulation as light sensor reading minus 50. Then we came up with our error correction mechanism by multiplying the error by the proportional gain and adding that to the speed as we have here. So that was added to the speed of motor A and subtracted from the speed of motor D. But before we control the motors, we want to add the error avoidance mechanism. So this is what I do. I'm going to delete the controls we had and leave it at the error detection. So let's see. Okay, so we have, this is the error detection formula. In the previous video we came up with a derived error, which was the error prediction formula. It was simply previous the error minus previous error. So to do that, we are going to introduce a variable that we'll use to keep the previous error. So I pick a variable. Let me name that previous error. So I add variable, I will say previous error. Okay, so we have a previous error variable. Initially there is no previous error, so before we start navigating, there is no previous error. But after our first iteration, the error that was recorded in the first iteration becomes the previous error. So to do that, I will say that before, so let's look at it this way. There is our error detection formula. Our error prediction was simply, that is the error, we read the error and then we read the previous error. So read, and then we will select previous error, and as we have here, it's error minus previous error. So I go for a math block, set it to subtraction, and then I have error minus previous error. So error minus previous error. So now we have our error detection formula here, and we have our error prediction formula here. Now we scale our detected error by multiplying the error by the proportional gain. So when we have this, let me make it simpler by saying we will introduce a variable and call it the derived error. So add a variable, call it derived error, and then we will store the predicted error in that container as derived error. So when we take the error, that's the detected error, and scale it by the proportional gain, we also need to scale the derived error by the derivative gain as we have in this formula. So the error is scaled by the proportional gain, then the derived error is scaled by the derivative gain, KD. So we will introduce another variable for KD. I would say add a variable for KD. So add variable, let's call it KD, derivative gain. Let us set it to an initial value of, let's say, a 10. I'll be explaining why KD is higher than the KP. So we would say that to scale the derived error, I take KD and I'm supposed to read its value and multiply that by the derived error. So I'd say derived error, I read its value, and then I'll multiply. So multiplication, so derived error, let me switch that. So I have KD, that is derivative gain, times the derived error. There was no need switching, as you know, multiplication is commutative. So now this is scaling my detected error, and this is scaling my predicted error. So error detection has been scaled, and then error predicted has also been scaled. Now from this formula, we are adding the scaled detected error and the scaled predicted error. So I'll pick a math block to add the two outputs. So I pick a math block and say that add the scaled detected error, predicted error to the scaled detected error. So now this is error detection and error prediction added. Then once that has been added, the result is the predicted, is a, let's say, a sum of the predicted and detected error. And that will be used to control the two motors. So what do I have to do? If I pick the motor on port A, it now has to move at a specific speed. So I'll pick the speed, the default speed. So I'll say the speed, I read the value of speed, and then it has to be added. So the speed plus the summation of the scaled detected error and scaled derived error. So I'd say I need to add, I pick a math block, and what do I add? Speed plus the summed or the cumulative sum of the predicted and detected error, and that goes to control motor A. And when I pick motor D, which has to then reduce when motor A is speeding up, so I take motor D, and then I would say motor D will also have to turn on, but its speed should be reduced, that is minus, and what am I subtracting? The same speed, but this time if A is speeding up, it should be slowing down by the same margin, that is the summation of the predicted, the scaled predicted and scaled detected error, and that goes to the motor on D. Then finally, before I end each iteration, I'll have to read the current error in this iteration and store it as previous error, so that in the next round the previous error will become the error that was used in the current iteration. So this implements error detection and correction as well as error avoidance. We have a default speed, and then a proportional gain to scale the detected error, a derivative gain to scale the predicted error. Our error detection formula is right here. That is light sensor reading minus 50. Our error prediction formula is right here. That is error minus the previous error, and it's stored as derived error. Then we scale the detected error by multiplying it by Kp, that's the proportional gain, and then we scale the derived error by multiplying it by derivative gain Kd, and then the sum of the two, the cumulative sum of the two, that's the predicted and the detected error, are added here. And then now the default speed is adjusted. Whenever we speed up motor A, we decrease motor D, and whenever we decrease the speed of motor A, we increase the speed of motor D, because the cumulative sum here is also a vector quantity which will either be a positive or a negative figure. So thank you for watching this video, and don't forget, before we ended, we had to store the current error into the container for previous error, so that in the next iteration that will be used as the previous error. Thank you for watching our video. Like, share, and comment. If you have any question, leave them as comments and we will address your question. My name is Michael Wilson, Chief Trainer for the Ghana Robotics Academy Foundation and the Chief Research Technologist at the Council for Scientific and Industrial Research, Ghana. See you in our next video. Thank you for watching. Bye-bye.